Hi, in this video, I'll give you a quick demonstration about the difference between a list and a Deque. Uh, More often, you will be using lists in Python. There are often times where Deque is recommended if you're going to be implementing a first in, first out queue. If you're new to Python, sometimes you might wonder how is it different, what makes list different than a Deque, or vice versa. So I will give you a quick demonstration so that you can understand as a layman how a Deque or a list really works. Hi, here's going to be an explanation on how a list can be visualized in a layman's analogy. Well, consider a list like these books stacked one on top of the other. Here what you see is a collection of books. This collection can be visualized as a list. Now we can consider this as the first book, which is the 0th index of the list. This happens to be the first index of the list, the second book, third index, and the fourth index. So you can start counting from bottom all the way to top. So that's how you visualize a list. The bottommost is the beginning, the topmost is the end. Now, when you look at a list as a stack of books, it's very easy to add a new book on top. Now, to add a new book on a list, you normally say list.append, right? And that's done like this. So it's very easy to add a new book here. And if you observe that I did not really have to change the position of any of these books, right? The index of these books are intact, no disturbance to these books. I was able to add a new book on top. I can add another book the same way by calling list.append of another book. And this is how a list is designed to work. It's designed to grow in one direction with minimal effort. In fact, if you want to remove a book from a list, remove an element from a list, right? The easiest way to remove an element would be the last element. So just like in the stack of books, it's very easy to remove the last element of this, right? Let's say I just removed one of the element. I can also remove one more element. This is the last element. Now I can remove this. This is what list.pop does. So when you say list.pop and don't pass any arguments to it, it just removes the last item from a list. Just like removing the last book from this stack of books that you see here. Now, there are some challenges with this. What if I want to add a book, not in the end? I want to add them in here, between this book, right? There's one Java book here, there's another Java book. I want to add another book in the midst here. So if you want to add a new book there, I might have to move these books across. What is like 0, 1, 2. The second index should become the third index. And the third index should become the fourth index. So make space here to add a new book. This is what insert does to a list. So when you actually say list dot insert of 2, an item, you're adding a new element in the midst. But at the cost of what? All the existing elements are reindexed. What was originally the index at the second, what is the element at the second index became third index, and what is the item at the third index has been reindexed to fourth index. So this elements have been moved up. Now the cost of adding this becomes more expensive as you grow down. For example, if to add a book in here, it was not very difficult. I was able to just move 2 books and add it across. It's not too very heavy. But if I want to add a book here, you can see it's getting more heavier, right? I could still manage it. I could actually add it in here. I could add this book in here. Now let's say I want to add one more book, right? I want to add another book, but I want to add this right in the beginning. Now this is going to be a little expensive because I have to make space right in the beginning to insert this new book, and this requires me to lift this up completely. And yes, it's quite heavy, right? So yeah, I still could manage it to some extent. Okay. I'm able to make space. So what exactly happened here? To occupy the 0th index, whatever element was there, the 0th index had to be shuffled to become first index, and first had to become second, third. So all the books had to be reindexed, all of them, right? And the cost is very high. If you have lots of books, if you have stacked up lots of books out here, it gets more heavier. So let's assume that there are already some books added. There are already some books added in here. Now this is very heavy. Let's say I want to add a new book right in the beginning. It's almost going to be impossible for me to do so. But by doing this, it gets too very heavy. Imagine having about 20 plus books stacked on top, and you want to add a book in the bottom, you need somebody else to help you out, right? But if you want to add a book on top, it's just straightforward. A list is a collection optimized for append and pop, not insert. If you want to insert, it gets very expensive as you grow down towards the beginning. Depends on the size of the list, right? So if you're trying to, let's say, insert a new element in a list of million items already, all these million items must be reindexed, and that is a cost, right? And this is what they talk about in the big O notation. They say O of 1 for append and pop, and O of n to insert in the beginning. So in effect, I could say that list is best used as a stack. Not exactly the stack. A stack is a last in, first out data structure. It's a collection where you insert elements in one order. The last element that you insert is the one that you're going to remove. So I'm going to show you an example. Like say, I added one book, right? This one, first item, second item, third item, fourth item. The last book I added here is the easiest to remove. Last in, first out. Last element in, first element out. What I added last but one, the penultimate item, that's going to be the second item I'm removing, right? You can see this. It's a last in, first out kind of data structure. Implementing a first in, first out kind of collection or data structure, we call them queues, is going to be very expensive in the list because either you have an insert complexity. If you have this stack of books again, it's not only difficult to add a new element at the beginning, it's also quite difficult to remove the element at the bottom. It's really easy to remove the element at the top, but imagine removing element at the bottom. More number of books on top, it becomes more effort, right? It takes more effort because of the weight of the book that is there. So the same cost, because all these books must be reindexed back, where the second book should become the first book, the third book should become the second book, and so on. So this is what you should visualize when you look at a list. A list is backed by a data structure known as vector. The most common perception or misconception rather by newbies in Python is that when they see the word list, they think it's made up of linked list. It's backed by a linked list. It is not backed by a linked list. It's backed by a vector, which is a dynamically growing array. So it can grow in one direction very easily, right? It can keep growing on top, or it can shrink from one direction. It's very difficult to grow by adding elements in the midst. So that's basically, there's an array that just grows or shrinks dynamically. So it's backed by a vector. But then consider this fact where I don't stack the books like this, but I stack the book in another way where I keep them like this. I'm sure that you would actually see many of you would organize your bookshelves where you organize books vertically in a bookshelf, right? Now this also is a collection. And this you can consider as a deck. A deck in Python is backed by a circular doubly linked list. But before I even go to the real implementation details, now just to give you an analogy of what kind of advantage deck gives you, just consider the books stacked vertically like this. Now here there are two ends. You can consider this as the beginning and this as the end. The left and the right. I'm going to call this left in my direction and right in this direction, right? So it's easy to remove a book from the end. You do it by using pop method. You can also add a new book at the end by using append method. So I'm able to use append and pop to add a book at this end. But it's also equally easy to remove the book from this end, which is beginning, right? The beginning part of the collection. I can remove this book here. I don't have to disturb any books that are already existing. You can also add a new book in here. To add a new book, maybe I'll add another book here. This is append left. This is pop left. A deck doesn't just have append and pop just like a list. It also has the ability to add or remove elements from the left side, which is done by using append left and pop left. Now this is what a deck is. A deck is an optimal data structure for implementing first in, first out queues. Now, if at all I want to represent a deck, in first out queue, consider this. I just have one book. I added one book into a deck, an empty deck. Then I can add another book. I can add another book. I can also add another book. So right now I added like 4 books. I added 4 books right now. Now to remove the books, I'm going to remove from this side. First in, first out. The first book that was in is the first book that I'm removing. So what do you do here? You add in the one end of the deck. You either use append left and you couple with pop. Append left to add elements to deck. Pop to remove elements from deck. Or you can do the other way. You could also use just append. You could use append. You could use append like this, right? And then I can say pop left to remove it. Pop left, and pop left. So even now you can see it works in the first in, first out order. A deck allows you to add or remove elements in either ends of it with minimal complexity, right? So though I show your deck this way, I told you it's backed by a circular doubly linked list. The best analogy of a circular doubly linked list is not like these books like this, but if you have seen this kind of circular bookshelves, rotating bookshelves, where you organize books in the rotating order. I couldn't find one. I don't have one here. All my bookshelves are like really flat. But then in my childhood days, I used to have audio CDs and music tapes organized in that rotary rack. Many of you in your childhood might have remembered or recollected, albums that way, right? But then I don't even have that. The closest I could actually bring about is another small, a small rotary rack that is used in the kitchen. So thanks to my wife, she just gave me this, but I'm just borrowing it with some random bottles. I'll just show you that. Oh yes. The closest approximation I can think right now, based on what I have, is this rotary rack that you see here. Okay, don't worry about the bottles. I could just randomly pick some bottles and put it in here. Think of them as each of them as items of this collection. You can consider this as a deck. You can consider this as a deck, right? So you have items in here. So the point is that let's assume that let's take this water bottle that I find here as the head of this deck. Now the head, you can see this is the second element, then there's third element, then the fourth element, and fifth element. It goes on all the way. And this is the end of a deck, and it comes just before the head, right? The tail of the linked list connects to the head. What's the advantage of this? Now on one end, you can see that if you really want to remove an element at the head, right? You want to remove an element at the head, you can just say pop left. Pop left removes this. Remove the water bottle. And now what happens is that this connects to this, right? This connects to this. I'm trying to make sure that these are all connected this way. If at all I want to remove an element, maybe not from the head. If at all I want to say remove an element at the end, I could call pop. Pop will just remove before the head. What is before the head? Is this, let's assume, I have a honey bottle. This is removed, right? So this space is removed. So this will be connected as the end now. If I say pop, what is before the head is removed. Pop, what is before the head is removed. Basically, the size of it will shrink. Make sure that the last element connects to the head. It's all linked list. One connects to the other, right? If at all I want to append, how do I append? You make space before the head. You make space before the head and you append an item before the head. Again, when you say append, what happens? You make space before the head and add an item. You can see that none of the other elements are shuffled across. Maybe, think of this rotary rack, right? Grows dynamically in size as you keep adding elements and shrinks in size, right? As you keep removing elements. That's how the deck grows and shrinks in memory. So you just add before the head to append, you remove before the head to pop, right? When you remove before the head, what was the previous element will become the last element by connecting to it. That's it. Just one time effort. None of these are disturbed. None of the other elements are disturbed. They're all just there in place, right? So on the other hand, instead of telling append, if I say append, instead of filling append and pop, if I say pop left will remove the water bottle itself. Now what is the water after this water bottle? I have this pepper sprinkler, and that's the first element now, right? You can see the honey bottle becomes the last element. It's connected to the head. Now this becomes a head. But if I now remove this by calling pop left, remember pop left removes this. Now this is connected this way. If I say append left, it is just going to add an element here. This becomes a head. What is the head, right? The head is this one. Append left will basically add an element before the head and make this the head. This becomes a head. There's only one cursor, which is pointing at the head, and before head and after head. You can see that, right? So you can add one more element this way, and this becomes a head. So you can see that the effort in adding or removing elements in a circular linked list is very minimal. You just add before the cursor or after the cursor, remove before the cursor or after the cursor, and that's about it. You just got to wire up one node before them. The neighboring nodes are wired up. Nothing else changes. It doesn't matter whether this particular collection had about 10 items, 1,000 items, or even 1,000,000 items. You can add in either ends or remove from either ends with minimal effort. There's also another interesting advantage of a circular linked list being used as a deck. And what is that advantage? Well, we all know about the advantage of circular racks, right? I'm in one direction. Right now, this is head to me. When I rotate it, this becomes a head. When I rotate it, this becomes a head. Right now, I'm rotating in one direction. Maybe it's clockwise in my direction, but okay. So if I rotate in other direction, let's say, this becomes a head. When this becomes a head, what happens to this? One before that becomes a tail. What is a head is second element, right? I can keep changing the head pointer by just rotating them like this. This is called deque.rotate. So deque also provides rotate in both directions. When I say rotate, it will rotate in one direction where the second element becomes the first element. No, sorry, the last element becomes the first element. When I say rotate, normally the last item becomes the first item. Let's assume that this is the first item, which is this, and this happens to be the last item. So when I rotate, what happens? Now this becomes the first item. What is the first item becomes second item. So now basically I just made the head point to this particular location. Again, when I say rotate, it's going to make the head point here. Again, the head points here. So you can actually iterate over all the elements of a deck without shuffling out elements just by rotating. Right? You can rotate and remove elements. You can rotate and add elements. So it becomes much more easier to work on a deck this way. In fact, round robin queues are implemented this way. Round robin queues are what? Let's say I want to process every single item in here. So to process every single item in here, my cursor is in just one direction. Right now, let's say the cursor is pointing in here. I want to process this item. So I just process this. Maybe I weigh it, pour some water, place it back. Now I'll rotate it. Now this becomes the first item. And rotate it. I process this item. I can add this back. Process this item. Add this back. So you're going to process item by item in a deck. It's very easy to just rotate, access the head, rotate, access the head. The head item is element at 0th index. Right? So this is how you visualize a deck. But one important thing actually about deck is that though it's easy to add in either ends of a deck, you can also do cheaper manipulation of deck by rotating them. Like you see this rotary rack, right? What is a drawback? A deck in reality, it's what is implemented in Python or the data structures. It's very difficult to go and get which is the 15th element. For example, I want to know which is the 15th element. I need to iteratively count it, this 1, 2, 3, 4, 5, 6. It has to go iteratively. You cannot directly hop onto 15th element. List, on the other hand, is backed by an array. If you know the space taken by each item of an array, you can simply do a math and just hop to the 15th index and get the elements. But a deck is like a linked list. You have each link which is connected to another link in memory, which could be in some other location, right? So there are complexities in here. In this example, I can't really show you that because all of them are contiguous, right? They look very contiguous. In reality, they're not really contiguous. This item could be located somewhere else. Okay, maybe the best way to analyze it is the items are not so contiguous. They're totally not contiguous. They could be connected through some links First item has a pointer to the second item has pointer to the third item has pointer to the fourth item. But these are not memory contiguous. They could be in different locations of memory. If you want to get one particular item from a deck, you should know the address of that item, and the address of the item is held by its neighbor, the previous item. So only when you know the head node, from the head you have to do a complete walk to reach that particular item. So that is a complexity. A deck is not used as random access collection. It's not optimized for random access. If I have a 100 million element deck, accessing the 0th element or 50 millionth element or 5,000th element, each of them, right? You cannot do it randomly. You cannot directly access them by indexing. You can use index operation, but indexing is very expensive. That is the reason why the built-in data structure for list is not a linked list like you see here for a deck, but it's actually implemented as a vector. Vectors are optimized for random access. A deck is only optimized for sequential access, used for FIFO kind of operations and round-robin queues. You can always create a list in Python. You'll know by using this particular syntax. There are three possible ways you can create most of the built-in collections. For a list, you can actually say A is equal to the literal notation, which involves open square bracket. You can have heterogeneous data. I have one of them is an integer, second one is a float, the third one could be a string. The fourth one could be a tuple, none, false, whatever you want, right? You can also have nested lists to suit your liking. Maybe I'll use some of the numbers here. This is one of the ways you can construct a list using literal notation. And as you can see, you can always add a new element to a list by using a dot append of another number, let's say 50. And when you look at what a is, you can see the value 50 being added at the end. If all you want to remove an element from the end of a list, you could always say a dot pop. Without any arguments, we'll always remove the last element. Some of you might ask, how about using the del keyword? Yes, you can also delete element from a list by using the del keyword. There's a subtle difference. Del is a statement, whereas a.pop is an expression. You could actually say something like this. You could say v is equal to a.pop. So whatever element was removed from that list is now represented by a variable v. The list will not have that element now. We can see the last item happens to be another list which got removed. The list shrunk by one item. But however, you can also delete an element by using del a of, you can say -1, last index, right? This also reduces an element in a list. It removes an element from a list, but it doesn't return anything because del is a statement. So you could see the list is having one element reduced. You can see one of the element is removed. But can you say v is equal to del a of -1? This will be a syntax error. One of the things you know about Python is that statements cannot be used as expressions. So all the keywords that make up statements cannot be used as a part of right answer expression, right? When I say all the keywords, I would say most keywords representing simple statements. So don't ask me how I can use if condition, I can use for in the right answer expression. The same keywords are being reused for statements and also expressions there. But in this case, del is a statement. So you cannot use it as an expression. This will be a syntax error. Now when you look at A, you could see nothing happens to this list. So you can add or remove at the end of a list by using this. Yes, if you want to remove from the beginning, you could say a.pop of 0 in this case. Removes the element from the beginning. If you want to add an element at the beginning, you have to use insert method. You have to say a.insert of whatever index, 0, let's say 100. And as I told you, that inserting a new item into a list involves shifting all these elements to the right. Basically, this would become the first index, this item would be the second index, and this item would be the third index. That's what insert does. I just demonstrated using the books analogy and how expensive this kind of operation could be. So if you want to insert an item anywhere in a list, you could use insert method. But if you simply want to add or remove element at the end, you can use append and pop. It's a very convenient way to do so. You can also remove an element from anywhere by using pop with an index being provided. Okay, so if you pass an index that is invalid, you'll get an index error. If you just try to say a.pop of 100, for example, you cannot pop out an item beyond the end of a list, right? So it throws an error in this case. Coming to a deck, you can always create a deck by using the collections module, Deque is not a built-in data type. So in order to use Deque, you need to say from collections import Deque. And now we can actually use D is equal to Deque of. You construct a Deque by using the Deque constructor this way, right? So you say Deque of and you provide numbers like this. I'm going to keep it very simple. A Deque is also fully heterogeneous. You can have first item as number, second item as string, third item as another Deque or another list. It's just like a list. It's fully heterogeneous, but then to keep things simple, I'm going to construct a Deque with just numbers in here. This is a Deque. A Deque is pretty much like a list in terms of the API. You can still say D of 0. You can index it. You can say D of -1. You can get the last element. You can say D of 3. Let me tell you a fact. This particular expression can become very expensive depending on the size of a Deque. If you have a Deque of 1,000,000 elements, if you say D of maybe 500,000, it's going to be very expensive because you cannot directly go to hop to 500,000 index and get an element from a Deque. It does a complete walk from the head till it reaches 500,000th element, right? So I would have told you that when I explained with that rotary rack of bottles, right? So it's the same concept here. So the way you create it, you can create it this way. So there are all these operations supported with different complexity. You could actually add a new item into a Deque by using d.append of 60, d.append of 70. So we add elements at the right side. If you want to add elements at the left side, you could say d.append left of maybe 25, d.append left of 30. You can see this. Elements added to the left. Likewise, you can remove from the right side of a Deque by using d.pop. You can pop out an element from the right side. If you want to pop out an element from the left side, the performance efficient way to do it is not telling d.pop of 0. Don't do this. It doesn't work, right? You can see that d.pop does not take any arguments. So you can only say pop with no arguments in a Deque. Or you can say d.pop left to actually remove the element from the left side. So we remove element from the beginning, right? So this is how Deque is designed. So you have append left, pop, and pop left. You also have rotate. For example, if you all look at this Deque right now, you have all these numbers which looks very orderly. The moment you say d.rotate, you can see what happens. The last element becomes the first element. You know what exactly happened? The head that was there just moved one step before. So before head there was a tail. So a tail becomes a head, right? So the cursor just moved. It's just like me rotating that particular rotary shelf and make sure that the cursor pointed to one bottle before it, right? So before the current bottle. So that's how it happened. So if you say d.rotate one more time, you can see what happens. You can also use d.rotate of -1. Rotate can take an argument indicating how many elements to rotate. If you give a negative number, it will rotate in a reverse direction. d.rotate of -1. See d.rotate of -1 one more time. Basically, the first element becomes the last element. Second element becomes the first element. You're rotating in that particular direction. You make sure the first element is at to the end. Therefore, the head now points to the second element, right? What was earlier the second element. So this is what Deque provides. So as I told you, these are the main methods: append left, pop left, and rotate. The extra methods that Deque supports. Beyond that, I think the Deque also has all the methods that you know in a list: append, clear, copy, count, extend. So all these methods just work like in a list. You'll find some methods like rotate. You have extend left. Extend left is to grow a Deque from the left side. Instead of using extend to grow to the right side, you can use extend to grow to the left side by adding another correction. So these are the concepts you should know in relation to a Deque, right? All the methods I showed you, and you'll find them in the collections module. In fact, when you try doing if you do import collections module, if you just try to say Deque with a question mark in IPython or Jupyter Notebook, you will actually get the complete details over here. In another video, I'm going to talk about what this maxlen is all about. This is a very interesting feature. I'll talk about this in another video, right? Thank you all. Hopefully, I hope you found this video useful in understanding the difference and semantics of a list versus Deque. Now you know exactly what data structure to use for what purpose, right? especially from the comparison from a list and a deck. Thank you all. If you do have any questions or further queries, please feel free to further add them in comments. And yeah, if you really like this video, do share with your friends if you might be interested in learning Python concepts as such. Thank you very much.